So, what we're going to talk about today, the most important things, a couple definitions. We've got eye level, picture plane, station point, cone of vision, center line of vision, and then obviously 1 and 2 point perspective. So, when we talk about eye level, essentially, eye level is just how far your eyes are from the ground. It's going to be different for all of you, and it will change based on whether you're sitting, standing, on a 10-story building, etc. So the picture plane, for all intents and purposes, is just the paper that you're drawing on. It could be a board, it could be your notepad, but essentially it's an imaginary field perpendicular to your station point that moves with your headset. So the picture plane is always in front of you, and for us it'll be our paper. The cone of vision, the way that your eyeball works, is light particles flood in at a certain angle, and everything within that angle is not distorted. Everything outside of your cone of vision falls into distortion. So the way to check that is hold your arms straight out in front of you and slowly expand them until you can no longer see them. That's your cone of vision. It's usually about 60 degrees, and station point is where we are standing, how close we are to the object. And that's important to know for when we map out this mechanical perspective on paper. The center line of vision is directly between your eyes and intersects your eye level at a perpendicular relationship. So then obviously 1 point perspective, all faces, all front facing planes of a cube or whatever it is, horizontals are always dead even, verticals are always perfectly upright. Obliques travel back to a singular vanishing point, which is at the crossroads of your center line of vision and your eye level. So let's get into 1 point perspective. So the way to start is we know where our eye level is based on cues from the world around us. So for just the purpose of a demo, we'll lay down a horizontal line. That's your eye level. Now, perpendicular to this eye level is going to be your center line of vision. So I am using all of these handy straight edges just for brevity. So what we're doing right now is we are mapping the mathematical perspective on a 2D plane looking above your viewer. So what that means is to project a 60-degree cone of vision. We flatten out the center line and eye level. And what we can do is take our handy dandy compass, and we will just arbitrarily mark out a cone. This is our flattened cone of vision. From here, we know that the cone of vision is 60 degrees. So I can take my 30, 60, 90 triangle, line it up to the edge here, project it down. So because these sides are going to be even, we know that the station point will be exactly where both of these 30-degree angles meet, combined to a 60. So here's our cone of vision flattened down. So we've got our cone of vision flattened down, and where this 60-degree, all right, you got to mute Marissa. Where this 60-degree cone of angle hits our station point on the center of vision. Now, the reason that the center and the eye level are so important is because that's how we know where planes are going to flatten out. So we're dealing with 1 point, and we want to have our vanishing point right where center and eye level converge. So right in the middle. Now, when we want to talk about picture plane, our picture plane is usually going to be within this cone of vision so that there's no distortion on our page. So real quick, I will just draw out a kind of proportion to it, 18 by 24. It's not exact. This is just for reference. So let's just say this is our picture, our piece of paper, fits within this cone of vision, and we've got our 1 point vanishing point. So from here, we can assume that all oblique edges will recede in this fashion. And what I can do now is I could say, throw in some verticals. I know it's 1 point, so my horizontals will be perfectly horizontal. My verticals are perfectly vertical. And now I can map in a couple angles. Now the important thing to remember is, as you can see, as we get closer to the center line of vision, the vertical planes on the sides of your object are flattening out. So if I were to say draw a cube farther away, I know that I'm going to see more of that side plane. So I can just kind of real quickly map these back. So the thing to remember is, aside from my wonky lines, we can translate verticals and horizontals throughout your cube because we know they're automatically going to be a certain angle. So like, for example, if I can say find the side of this cube, and it's not a cube, in space it's actually a rectangle. But because I found this arbitrary vertical, I can transfer a horizontal line to find the top. And likewise, since we're drawing volumetrically, I can take this bottom corner and send it right back to the vanishing point. Now, how do I find this invisible edge that we can't see the cube? Well, that's easy. We already know where this corner is. So we extend it horizontally. And now, if we did it right, we can extend it vertically, and it should match up to that top corner. So that's 1 point. Now, as you see, as you move closer to the horizon line, you're going to see more flattening of the planes. So I'll draw one, for example, on the horizon line, and we'll draw one pretty far above. So I know that this front is going to be square because we got to obey the rules of 1 point. So essentially this bottom face here is just going to extend right back to the vanishing point, whereas these sides here will have diminishment. So because we can't see this bottom plane, it's right on the eye level, we can still add in an edge on the left, and I can still carry this line horizontally. And because we have these two converging lines, I can still put in that vertical. So this is all just the illusion of space. And let's say we can put one a little farther out. We're still within the cone, but right now we're outside of our paper. And I'll show you, this will take us outside of our cone of vision and it will become distorted. So in general, we want to avoid this, but I just want to show you. So we've got the cube or the square, and let's just say drop in a horizontal, take that vertical up, and I can just march along and fill in the blanks. So 1 point perspective in a nutshell. This will be part of your homework for this week, the 6 cubes in 1 point. And I will show you a couple rules. If you have the same scene, you absolutely cannot have 2 different 1 point vanishing points. If it's the same picture, you've got to put that vanishing point right at the convergence of center line of vision and eye level. You can't have 2 1 point in the same in the same drawing. You can have multiple 2-point setups, but you cannot have multiple 1-point. So one way to kind of figure out if you're looking head on at a cube and you need to figure out what's going on with the perspective, or let's say you just want to make an interesting scene, pick 2 points where they converge within a square or a rectilinear surface. So I'm going to arbitrarily pick this line, we'll connect the dots. Now because I've chosen those, this dot can extend back to the other corners. And the reason is now this chosen point becomes my center line of vision. And we know that the eye level is perpendicular. So now we've got a setup. And then if we want to reverse engineer this to make it mathematically sound, you just grab your 30, 60, 90, and we can kind of pick, we'll just say, we'll throw a station point in just because we can. So there's our 30, there's our 30. Grab our handy dandy protractor, and we can already see that I'm a little outside of the cone of vision. So you want to make sure that you extend out far enough to encompass your whole picture. So let's talk a little bit about 2-point. So 2-point perspective has a similar rule in that verticals must be completely up and down. However, your sides will diminish to their respective vanishing points, and depending on how drastic one side is, the other side will be more slight. What I mean by that, I'll go through a quick setup real quick. We got our eye level. We know our center line of vision is perpendicular. So we want to make sure we give ourselves enough space for doing this mathematical 2-point because this gets a little wider on the page just by the nature of the vanishing points. So let's just go real quick. Cone of vision. Let's do back to our station point. And what I want to explain is just the radiating nature of vanishing points and how they flatten out at the eye level. So we've got our station point, we've got center line of vision, we've got cone, and then this is our eye level horizon line. That's the same for 1-point. 1-point and 2-point, eye level and horizon are the same. That's what allows our verticals to be completely up and down. So here's the tricky part, right? Vanishing points in 2-point perspective are at a 90-degree relationship at the station point. What does that mean? That means if I want to pick arbitrarily an angle for one vanishing point, the other will be predetermined based on my station point. So I'll just show you real quick. So what I'm doing here is showing the relationship with moving the triangle. And so as one becomes more drastic, the other one becomes more slight. We'll pick an arbitrary point that will fit on our page just because we don't want to add more paper right now. So I'm going to say, let's just take this point on the right as our vanishing point. I will draw an arbitrary line into space. So this point here will be the front corner of our approximate cube. So because I've got that, I can say all obliques go back to this vanishing point. Now I have a plane for all intents and purposes. Here's a plane. And we'll say, okay, so how do I find the other vanishing point? That's easy. Take my triangle again, I line it up, draw a line from my arbitrary vanishing point down to my station point, and I know that there's a 90-degree relationship between my left and right vanishing point. So this VP is right at the cusp of the cone of vision. So we'll do VP1, we'll do VP2, and now all the lines going to the left will converge at this vanishing point. So, like we said, there can be different sets of vanishing points per 2 point, but not for 1 point. And so we're drawing volumetrically. We want to go through this, and we'll just arbitrarily pick side of the cube here. So once we kind of figure out that vertical, that's our known. We can figure out our unknowns and just take that corner that we created and take that back. So now we've got this cube in space within the cone of vision. And just to add it in, I'll just throw in a picture plane. Let's say our composition is, you know, something just within the realm. So here we go. This might be our page of paper, and you've got your eye level established with the proper diminishment. Now, if we wanted to, we could go over this and add a different set of vanishing points using the same setup. So real quick, just tape this up together. What I can do, call out our eye level again. Eye level, center line of vision. We know where our station point is. Just draw the cone in just because. So just so you can see it, here's our original cube right in here. And now if we wanted to draw another cube at a different angle, all we have to do is rotate a new set of vanishing points. So because we went far to the right, we'll go over here, other side, and I'll just say bam, bam. Here's my second set of vanishing points. This is still my cone of vision. Just draw this in because we can. So if we wanted to do a new cube at a different perspective, we'll just travel with a new set of lines, and we'll make him about right there. Now extend back to the right. We've already got our edge here. Here's this, back to the right. If we want to kind of give him a little space, this is kind of a skinnier block, and this is pretty much it. So then I can take this point back here, and now I've got two rectilinear objects at different perspective on the same field. So when you're doing your homework, you will be able to rotate the blocks into point and just keep the verticals aligned. Now, what else can I talk about? All right, I'm going to end the recording here.